let me mention a few things about that. Well, we have a proposition, which is that if G is a planar graph, which is somehow embedded in the plane already, and you take the planar dual, then the matroid of G, the dual of the matroid of G is the matroid of G star, of the dual of G. Yeah, and in particular, so in particular, M sub G is called a graphical matroid. While its dual is, well, so if this is for G an arbitrary graph, not necessarily planar, then this is called a graphical matroid, and this is called co-graphical. So in the sense, the dual of an arbitrary graph is a co-graphical matroid. That's basically the terminology here, and this is not always graphical. So if your graph is non-planar, then this is some other object which is sort of as nice as the class of graph. The co-graphical matroids are sort of just dual to graphs. And yes, so the way to think about graphical matroids in general is vague idea is that if you have a graphical matroid, then it basically it can see only the edges but not the vertices of your graph. I don't know how to state this precisely mathematically, but the idea is that it knows about such things as edges, cycles, trees, etc., but not about vertices. So we can't, and yeah, there's no known way to define vertices of a graph from a matroid. And finally, let me mention one more cute corollary of this result. Corollary. It's Euler's formula. So if G is a planar graph, then has vertices, edges, and faces. And as you know, vertices minus edges plus faces is what? 2. Okay. How do you prove it using this statement here? This is tricky. All right. Yeah. So what is the rank of M sub G? Or in general, let's say I give you a matroid. What is, by definition, what is the rank matroid? Size of any basis. Nice. What are bases of the graphical matroid? Spanning forests or trees? Spanning trees. Okay. But yeah, the graph has to be connected. Oops. Okay. So what is the rank of the corresponding matroid? Number for what? V minus 1. Okay. All right. what is the rank of the dual, well, of the dual graphical matrix? If I take the dual graph and then I look at the matroid, what's the rank going to be? F minus 1. Okay, what's the relation between the two ranks? Right, okay, so if you take the sum of these two ranks, you are going to get the size of the ground set, which is E. So there you go. All right. Any questions on this? All right. So, and yeah, as we mentioned here, so in general, if M is any matroid, then the rank of the dual is the size of the ground set minus the rank of your original matroid. So in particular, yeah, now I want to talk about vector configuration. So let's say V is a configuration of vectors. And yes, so I'm assuming that all my graphs are connected. I'm also assuming that all my vector configurations span R to the D. And span of V is R to the D. So yeah, now I want to talk about the matroid. Let's say I take the M, let M be the corresponding matroid. So the basis of M are the collections of vectors here that form a basis. And then the question is the dual realizable over R, let's say? What do you think? Okay. Right, okay, so you want, the natural guess is that if that's a dual matrix, so you need to take the dual of this linear space, which is also d-dimensional, which, by the way, so what's the rank of M star? It's n minus d. So if it is realizable, it should be some collection of vectors in the n minus d dimensional space. That's a mystery. How do you, like, you can't really stay within R to D. You can't like take orthogonal complements to these vectors and do some stuff with those. You have to actually, and yet somehow n minus d seems sort of orthogonal to D. Yeah, anyways, that's what I'm gonna, to explain this, I actually have to introduce some stuff. Yeah, the answer is yes. What? Yeah, okay, you're happy. I'm happy too. Okay, so how do I explain this duality in terms of vector configurations? And for that, I'm going to need to discuss the Grassmannian. Because this duality here happens to be a special case of Grassmannian duality. So, and this is going to be a quick introduction into the Grassmannian. So you take, I guess, what is D here, I'm used to denoting by K in the Grassmannian world. So you choose two integers K and N. K is less than N. And then the Grassmannian is the set of all linear K-dimensional subspaces of R to the N. Okay, this is linear subspace. For example, if I take K equals to 1, 1, N, I get the space of all lines inside the n-dimensional space. That's the projective space. Rp n-1. Yeah. So in particular, let's say I choose some element of the Grassmannians. This is, if you haven't seen this before, it's a nice, compact, differentiable manifold. It's very nice topologically, sort of algebraic variety, all kinds of words. But so let's say I pick a point on this space, which is a linear subspace of R to the n. Let's say I choose a subspace U. Then I can choose a basis of the space. Basis is going to be choose basis U1 go after U, K in U. And what I'm going to do is I'm going to write them as a matrix. So what I'm going to have is U is the row span of a matrix where the first row is U1, then U2, etc., all the way up to UK. It's a K by N matrix. It's K by N matrix of full rank. And of course, I could choose a different basis. A given linear space has many different bases. And how are they all? How are the corresponding matrices going to be related? Yeah, but action by an invertible matrix on which side? On the left, right? Yeah. So if you apply invertible row operations to these matrices, you get all possible bases of it. So the other way to think about the Grassmannian is just full rank K by N matrices modulo row operations. And yeah, and so row operations correspond to change of bases, and also, yeah, and it's the same as the action on the left by left action of the space of G, yeah, is noted GLK, space of K by K invertible matrix. Yeah, it doesn't really matter, but the point is that you think of subspaces in terms of matrices. And now what I want to, how do I relate this to matroids? Let's say I give you a subspace U. How do I associate a matroid to the U? The ideas. Oh, interesting. You want to take a matrix and then you want to take the columns. Interesting. But then the columns are, I mean, if I choose a different basis, I'm going to get different columns. It looks like it's not well defined, right? Or yeah, let's actually record this. This is interesting. So let's say I fix U, which is the row span of some matrix A. K by N matrix. Then let's say I look at the columns. V1, Vn, with the columns of A. And okay, so they do span the whole space. Right? So it's a vector configuration in R to the K times N, and the span. Why is the span of V the whole space R to the K? the definition. Which definition? Right, okay, so the rows form a basis of r to the n. Well, the rows form a basis of u. But if you look at the columns, because it's full rank, the columns do span the whole space. Okay, and then you look at the corresponding matroid. And of course, the vectors depend on the choice of the matrix. But the claim is that the corresponding matroid depends only on u. I see. So you're saying, yeah, you're telling me the proof of the. Yeah, let's record the proof. The proof is that if I look at the matrix, I'm going to decide which collections of columns form a basis of my matroid. So the basis of my matroid are the set of all I subset bracket n, such that the size of, so I'm looking at k element collections of columns, such that the corresponding vectors vi, where I is the set, form a basis. So what does it mean in terms of matrices? Well, it means that the determinant of vi, I is in I, is non-zero. This is the condition that the given collection of k columns forms a basis of the matroid. And the claim is that this determinant is invariant. Well, the condition that it's non-zero is invariant under invertible row operations. So another way to think about this is, if you look at the columns of your matrix, they live in R to the k, and if you apply a change of basis, that means you apply a global linear transformation to R to the k. So whether some vectors lie on a line or something, it doesn't depend on the choice of coordinates, basically. Row operations correspond to choice of coordinates in R to the k. So in particular, since this matroid depends only on my subspace U, every element of the Grassmannian has the associated matroid. I'm going to denote M sub U as this M sub V, matroid associated to U. Okay, so is this matroid realizable? Yeah. Right. Yeah, it's given, it comes from a vector configuration, so it's realizable over R. What's the rank of this matroid? The rank is equal to k. Okay. All right. So yeah, for every point in the Grassmannian, you get a matroid. So it's called the Matroid stratification of the Grassmannian, which by definition is, you take the Grassmannian Kn and you subdivide it into these subsets. You write as a disjoint union over all matroids of X sub m, where X sub m is the set of all U inside the Grassmannian, such that the set of all points U which have the given matroid M. Right? We have the whole Grassmannian subdivided into these little pieces, and do you think these pieces are nice or, well, first of all, if you take an arbitrary matroid, then the piece is going to be empty whenever your matroid is non-realizable. These pieces actually know about realizability over R. And do you think they are, do you think these are nice as topological spaces, or do you think they are not nice? Feeling. Yeah, okay, they should be algebraic varieties. That is true. Should they be like homeomorphic to some nice things, or should they be open balls or something, maybe? Or can they have non-trivial loops inside of them? Should be some loops. Yeah, is this a CW complex, for example? Or, okay. Yeah, so the actual reality is the opposite of what we just discussed. These pieces are super bad. There is something called Manov Universality theorem, which so let's see, what do they tell you? It tells you that X of M, these pieces have arbitrarily bad topology. And so it is true that these are algebraic varieties, right? They are defined by polynomial equations. It's not clear from what I just said that they can be given by polynomial equations, but there's something called the Plucker embedding, which tells you that each piece is an algebraic variety. But yeah, if you don't know about algebraic varieties, you can skip whatever I'm saying right now. But the claim is that for any affine algebraic variety, so take a bunch of multivariate polynomials and set them all to 0, and look at the set of solutions for any affine algebraic variety, y, which is defined, so the coefficients of the polynomial should be rational numbers. The claim is that there exists a matroid M such that the corresponding piece is isomorphic to y, as in like it's homeomorphic to y, and isomorphic as an algebraic variety. And this is yeah, algebraic varieties are not very nice. You can basically cook up any topological space you want by taking enough polynomials. So this is, yeah, you can like write your name like using polynomial equations, and then there is a matroid who's, so this is called like the realization space of the matroid. And yeah, so there is a matroid for any kind of topological space which can be obtained this way. Yeah, so this is Manov. Yeah, this stratification is due to Gelfand, Goreski, McPherson, Serganova, 87. This is due to Manov, I think, a few years later. So yeah, these are, and yeah, in this paper, they actually hoped that these pieces would be nice, as you hoped like 5 minutes ago, but turns out that these are very bad. Okay, so going back to the duality question. If I have an element U of the Grassmannian, then I get a matroid. What is the dual of this matroid? Transpose which matrix? Okay, so interesting. U is the row span of a K by N matrix. Okay, so if I take the transpose, I'm going to get N by K. Okay, yeah, okay, so you want to take N by K with action on the right. So you can act by GL K on the right. Then what? Yeah, how do we get the rank N minus K from this picture? Okay, so let's assume. Okay, let's say U is super good, which means that you're saying it means that the first K columns form a basis. And then I can apply row operations to make the first K columns look like this. And then this is matrix, some matrix A. K, N minus K. So A is indeed K by N minus K. If you draw A transpose, it's going to be N minus K by K. And then what do I do? So if I take the columns, I'm going to get K vectors. Yeah, these vectors are going to be all linearly independent because the rows of my matrix are linearly independent. Okay, yeah, so, and this is actually, this is on the right track. There is a way to make this work, namely you have to add the identity matrix here and change some signs. But, right, so you know the first K columns form a basis, so the last N minus K columns here should form a basis. This seems on the right track. Let's say you forget about the matrix and just look at the subspace. What? Yeah, I want you to guess this one. Take its orthogonal complement. That is correct. Right, so this N minus K, this N minus K. So take the orthogonal complement, which is a point inside the, it's an N minus, if this is K dimensional, this is going to be N minus K dimensional. And so there is a matroid which is associated to this. There's a unique matroid associated to this space. Position is that the matroid of U perp is the dual of the matroid of U. Proof exercise. Oh, I should mention the homework. Homework number 2 will be released today. It's going to be due in a couple of weeks from now, so at the last lecture. The rest of the 2 weeks to solve the problems. And yeah, and by the way, so some people did very well in the first homework, some people did like less well, but also fine. And so I guess there's homework number 1, which had 5 problems. Homework 2 is also going to have 5 problems. Actually, many more problems, but you can choose up to 5. And then I guess I'm gonna to get the maximum score, like to get an A, you need to solve 8 problems total. Each problem is 10 points. You need 80 points. That's what I'm saying. So if you got the perfect score in the first homework, you can solve 3 problems instead of 5 for the second homework. Any questions on? So this is due December 3rd. And this is not intended to replace your Thanksgiving break. Please have some rest during Thanksgiving, and then yeah, this is not going to be too intense. In particular, if you start with my original question, have some vector configuration in R to the D, then the way to get the dual matroid is you put them in a matrix as columns of a matrix, and then take the row span from that matrix, take the orthogonal complement, and then look at the columns. So that gives you the dual matroid. And perhaps I should give an example. Here's an example. Let's say I take a point in Grassmannian 1, 3. It's the row span of a 1 by 3 matrix. Let's say my matrix is, so if it's completely generic, that's not as interesting. Let me make it slightly non-generic. 1, 0, and x. These are, the column vectors are v1, v2, v3. And what's the orthogonal complement? Zero x density matrix. Okay, so in order for this row span to be the orthogonal complement of this row span, the dot product of this row should be 0 with this row and with this row. -1 or -x. Yeah, you have to introduce, when you transpose this matrix, you have to introduce some sign. And then it becomes orthogonal. In particular, yeah, so the picture here is, this is a matroid of rank 1. V1 looks like this, and then V2 is 0, and then V3 is x times V1, and then U1, U2, or maybe W1, W2, W3. These are two-dimensional. So 0, -x, this is W1. 1, 0 is W2, and then 0, 1 is W3. Okay. In particular, V1 forms a basis here, so V2 and V3 form a basis here. And V2 does not form a basis, and therefore its complement, W1, W3, do not form a basis. Okay? So the basis of this picture are complements of the basis of this picture. Yeah? So if you want to, so basis-free explanation of this stuff. I mean, if you talk about matrices, you have to use some of the axiomatization. You can talk about maybe independent sets, or which are not that different from basis, or maybe circuits. Yeah, so it's, I mean, either way, you're going to have to basically fixing a matrix corresponds to choosing some vectors, and then you can, yeah, I don't know how to talk, how to. Oh, this is true over any field. You can have inner product over any field. Yeah, and this will say wait, hold on, let me think about it. I think this works over any field, and in particular, you're saying we could have non-zero vectors which are orthogonal to each other in over a field. Yeah, let me actually think about it. I thought this would work over any field. Yeah, I have to think. Yeah, this is a good question. I thought I knew this answer, but maybe I don't. All right, I'll think about it. Yeah, I'll mention this on Wednesday. Yeah, all right. So one last, well, not last, but the next thing I want to mention about Matroids, we discussed Matroid duality. Let me now try to explain how they generalize hyperplane arrangements. In particular, we had this nice characteristic polynomial for hyperplane arrangements. What happens for Matroids? And for Matroids, we have what is called the lattice of flats. So first of all, let me mention another way to think about Matroids, which is in terms of the rank function. The rank function Rk from, so to every possible set, subset of your ground set, you associate a rank, which is some non-zero, well, some non-negative integer. By definition, so x is a subset of your ground set, then the rank x, so I'm given a matroid. So let's say M is a matroid. Then the rank function of M of x is by definition is the maximum size of an independent set, which is contained in X. Okay, so for any, if you have a bunch of vectors, then the rank is just the dimension of the space they span. And in particular, we have the following properties of the rank function. And again, you should think of this as axioms, which give you another definition of the matroid. And as usual, some axioms, most axioms are going to be trivial. First one is that the rank is between 0 and the size of x. The second axiom is that if you have two sets, x and y, and x is contained in y, then the rank x is less than or equal to the rank of y. X is contained in y. And finally, there is what would be an interesting axiom of the rank. Function. This should be kind of like the exchange axiom, except that it's going to look slightly different. So you have any two sets, x and y. Then there should be some condition on the corresponding rank function. I see. So you want. Yeah, I think what you're saying could be made to work. It could be made similar to the basis. But the actual. Okay. Okay. Yeah, that's That's also, yeah, I think both of these should work basically because this is defined in terms of independent sets. Yeah. And actually, yeah. Any other guesses? No. Yeah, let me write down the condition. So the condition is that the rank of X, sure. Yeah, go ahead. What? Oh, I don't know who just said that. Oh, all right. Oh, sorry. Sure. Yeah. Maximum. Yeah, thanks. Doesn't commute. All right. No more guesses. The rank of X intersect Y plus the rank of X union Y should be less than or equal to the rank of X plus the rank of Y. Which, yes, so what you propose, this is also, I think, fine, but this is also fine because there's no quantifiers. There's no, for each I, there exists a J, just inequality like that. And in particular, yeah, so these three are true for matroids, and conversely, if you have these properties, then the rank function defines a matroid. And so we get another axiomatization in our toolbox, which we're going to use now to define flats of a matroid. So what is a flat? A flat of a matroid M is a set F. It's a set where you can't, basically, if you add any other element, the rank goes up. So the picture you should think of is if you have a matroid like this, then these 3 points form a flat. Any 2 points don't form a flat. Any 2 points on this line do not form a flat. It's a set F, subset E, such that the rank of F union X is strictly bigger than the rank of F for all X not in F. Okay. So these are like maximal by inclusion sets of a given rank. And but in particular, let me introduce the Paul set of all flats. Paul set of all flats of M ordered by inclusion. Let's say I have an example like this. 1, 2, 3, 4 equals to 5. Then what would be the lattice of flats? What's the minimal element? The minimal element is the empty set. Which elements cover the empty set? A set containing both 4 and 5, and also the other singletons. 1, 2, 3, and 4, 5. All right. What's the next row? 1, 2, 3, 1, 4, 5. 3, 4, 5. Anything else? Okay, yeah, so you look at two-dimensional flats. And this is one flat, 1, 2, 3. And then there's another one, 1, 4, 5, 2, 4, 5, and 4, 5. 1, 2, 3, 1, 4, 5, 2, 4, 5. Finally, what goes here? 1, 2, 3, 4, 5. Perfect. Okay, so why is it called the lattice of flats? Probably. I think they're just moving stuff in the next room. But if you're scared, you could sit up front. All right. So okay, should we continue or should we? Okay. So indeed, the lattice of flats is a lattice. Proof. Exercise. So yeah, I'm guessing the meet of two flats is easy. Therefore, you are done by, because the lattice is fine. There's some way to prove that things are lattices. And here's another proposition, which is that let's say you take a central hyperplane arrangement. Central hyperplane arrangement. Then what's the connection between the, here we had the intersection lattice. And then, so there is, on the one hand, there is the intersection lattice of A. And then also there is the, you can take the matroid of A and take the lattice of flats. What's the relationship between the two? They're equal. Or actually, so what's the definition of the lattice of the intersection lattice of A? I mean, all right, never mind. These are equal. Yes, so here the possible source of confusion is that here, this is the, so what is L of A? It's the set of all intersections of hyperplanes in A, which are ordered by reverse inclusion. But the flats are ordered just by inclusion. So why are these two? Yeah, what's the bijection between the two? Between the flats of a matroid and intersection lattice of hyperplane array? Okay, right. So you're, yeah, basically the idea is that if you have, I mean, you're right. So the bijection is that if you have a bunch of hyperplanes, so X is H1 intersect H2 intersect HK of a bunch of hyperplanes in A, then you can take, well, actually it's the other way around. If you take a flat, okay, I'm out of time. All right, never mind. There's a bijection where you take a flat of this matroid, and then take the orthogonal complements of the vectors and intersect. And then you get an element of the intersection lattice, and every element you get in particular. Yeah, so this is the isomorphism. But anyways, I'm going to see you all on Wednesday, and Friday is a holiday.